The deeper implications of all objects spinning or rotating in our universe. How it could make us misunderstand simple phenomenon and what new phenomenon it could create. How it's related to entropy and energy that leads to the cosmological constant. Spin is an intrinsic property of elementary particles and objects in the universe, which describes the rotational motion of those objects around their axis. The spin of an object is usually measured in terms of its angular momentum, which is a vector quantity that describes the amount of rotation of the object around its axis. Objects in the universe exhibit different types of spin, depending on their size, mass, and composition. For example, planets and stars have spin, and the direction and rate of their spin can have significant effects on their structure and behavior. The direction of spin is often referred to as clockwise or counterclockwise when viewed from a certain direction. However, since there is no universal up or down in space, scientists use a right-hand rule to determine the direction of spin. This means that if you curl the fingers of your right hand in the direction of spin, your thumb will point in the direction of the object's angular momentum vector. Interestingly, some astronomical objects, such as black holes and neutron stars, have extremely high spin rates, which can have significant effects on their behavior. For example, the spin of a black hole can create a strong gravitational field, which can cause matter and radiation to be ejected at high speeds in jets perpendicular to the black hole's spin axis. 1. The different classifications of spin in particles and the mathematical formula that describes it. In particle physics, the spin of a particle is classified in terms of its intrinsic angular momentum, which is a quantum mechanical property. There are two types of particles, bosons and fermions, and the spin of each type is described differently. Bosons have integer spin, which means their spin can take on values of 0, 1, 2, and so on. Examples of bosons include the photon, the W and Z bosons, and the Higgs boson. Fermions, on the other hand, have half-integer spin, which means their spin can take on values of 1/2, 3/2, 5/2, and so on. Examples of fermions include electrons, protons, and neutrons. The mathematical formula to describe spin is given by the spin operator, which is a vector operator that acts on the wave function of a particle. For a spin 1/2 particle, such as an electron, the spin operator is given by the Pauli matrices S_x equals bar/2 asterisk sigma _x, S_y equals bar/2 asterisk sigma _y, S_z equals bar/2 asterisk sigma _z, where bar is the reduced Planck constant, and sigma _x, sigma _y, and sigma _z are the Pauli matrices. The spin operator can be used to measure the spin of a particle along different axes, and it is an important tool in quantum mechanics and particle physics. The spin of a particle can also be described by its spin quantum number, which is denoted by S. For a spin 1/2 particle, the spin quantum number is S equals 1/2, while for a spin 1 particle, the spin quantum number is S equals 1, and so on. The spin quantum number determines the number of allowed spin states for a particle, which is given by 2s plus 1. For example, a spin 1/2 particle has 2 allowed spin states, while a spin 1 particle has 3 allowed spin states. 2. How the spin of a particle affects the spin of another particle and the mathematical formula that describes it. The spin of one particle can affect the spin of another particle through a process called spin-spin interaction. This interaction arises due to the magnetic moments associated with the particles' spins, which can interact with each other and cause them to align or anti-align with respect to each other. The spin-spin interaction is described mathematically by the Hamiltonian of the system, which includes terms for the spin operators of each particle and the interaction between them. For example, the Hamiltonian for two spin 1/2 particles can be written as H equals H1 plus H2 plus H12, where H1 and H2 are the Hamiltonians for the individual particles, and H12 is the interaction Hamiltonian between them. The interaction Hamiltonian is given by H12 equals J, S1, S2. where J is the strength of the interaction, and S1 and S2 are the spin operators for the two particles. The dot product represents the scalar product between the two spin vectors, which determines the alignment or anti-alignment of the spins. The spin-spin interaction can lead to a variety of interesting phenomena, such as the exchange interaction, where the spin states of the particles exchange with each other, and spin entanglement, where the spin states of the particles become correlated and cannot be described independently. In addition to spin-spin interaction, particles with spin can also interact with external magnetic fields, which can cause their spins to precess or change direction. This is described by the Larmor equation, which relates the precession frequency of the spin to the strength of the magnetic field. The interaction of multiple particles with spin can be described mathematically using the concept of a spin Hamiltonian. The spin Hamiltonian describes the total energy of the system in terms of the spin operators of each particle and their interactions with each other. For a system of n particles with spin, the spin Hamiltonian can be written as H equals H1 plus H2 plus Hn plus H12 plus H13 plus Hn1n, where Hi is the Hamiltonian for the ith particle, and Hij is the interaction Hamiltonian between particles I and J. The interaction Hamiltonian between particles I and J is given by Hij equals Jij, Si, Sj, where Jij is the strength of the interaction between particles I and J, and Si and Sj are their spin operators. The dot product represents the scalar product between the two spin vectors, which determines the alignment or anti-alignment of the spins. The total spin of the system is given by the vector sum of the individual spins of each particle. The eigenstates of the spin Hamiltonian correspond to the different spin configurations of the system, and the eigenvalues correspond to their corresponding energies. The spin Hamiltonian can be solved numerically or analytically to determine the behavior of the system. The solution can reveal interesting phenomena such as spin ordering, where the spins of the particles align in a particular direction, or spin frustration, where the spins cannot align due to competing interactions. 3. Why particles spin to begin with? Particles in quantum mechanics have intrinsic angular momentum, which we call spin. Spin is a fundamental property of quantum particles, just like mass and charge, and is an essential part of our understanding of the structure and behavior of matter. The existence of spin was first postulated by Wolfgang Pauli in the 1920s to explain certain experimental results that could not be accounted for by the properties of known particles, such as electrons and protons. The idea of spin was further developed by Paul Dirac and other pioneers of quantum mechanics. One of the key reasons that particles have to spin is to satisfy the principles of quantum mechanics. In quantum mechanics, particles are described by wave functions that can have different values of angular momentum. In order to be consistent with the laws of quantum mechanics, the wave function for a particle must be a linear combination of different angular momentum states, including spin states. Another reason that particles have to spin is to explain certain experimental phenomena, such as the magnetic moment of the electron and the Zeeman effect. The magnetic moment of the electron arises from its intrinsic spin, and the Zeeman effect is the splitting of spectral lines in the presence of a magnetic field, which can be explained by the interaction between the magnetic field and the spin of the particles. Finally, spin plays an important role in the structure and behavior of matter at a fundamental level. For example, the Pauli exclusion principle, which states that no two identical fermions can occupy the same quantum state, is a consequence of the fact that fermions have half-integer spin. This principle is essential for understanding the stability of matter and the properties of materials. 4. Electrons' motion in space without the influence of the nucleus. The motion of an electron in space away from a nucleus is governed by the principles of quantum mechanics. In quantum mechanics, the motion of particles is described by wave functions, which are complex mathematical functions that describe the probability of finding the electron in a particular location in space. As an electron moves away from a nucleus, its wave function changes, and the probability of finding the electron in different locations in space changes accordingly. The wave function for an electron in free space is a plane wave, which means that the probability of finding the electron is evenly distributed over all of space. However, the motion of an electron in free space is not completely uniform, due to the effects of wave-particle duality and the uncertainty principle. These effects cause the wave function to spread out over time, so that the probability of finding the electron becomes less and less certain. In addition, the motion of an electron in free space can also be affected by external forces, such as electric or magnetic fields. These forces can cause the electron to accelerate or change direction, leading to complex and often unpredictable behavior. The motion of an electron in space is described by the Schrödinger equation, which is the fundamental equation of quantum mechanics. The Schrödinger equation describes the evolution of the electron's wave function over time and is given by I psi/t equals h psi. Where is the reduced Planck constant? T is time, psi is the electron's wave function, and h is the Hamiltonian operator, which represents the total energy of the system. The Hamiltonian operator is given by h equals dash superscript 2/2m, superscript 2 plus v, r. Where m is the mass of the electron, superscript 2 is the Laplacian operator, which describes the curvature of space, and v, r, is the potential energy of the system, which includes the effects of the electric and magnetic fields that the electron may encounter. The solution to the Schrödinger equation gives the wave function of the electron at any given time, which can be used to calculate the probability of finding the electron at a particular location in space. The wave function can also be used to calculate other properties of the electron, such as its energy, momentum, and angular momentum. 5. The motion of large objects in the universe and the cosmic microwave background. The cosmic microwave background, CMB, is a faint, uniform glow of radiation that pervades the entire universe and is thought to be the remnant of the Big Bang. The CMB can be measured using a variety of instruments, including ground-based and space-based telescopes. One of the most famous experiments that measured the CMB is the Wilkinson Microwave Anisotropy Probe, WMAP, which was launched by NASA in 2001. The WMAP satellite measured the temperature of the CMB to high precision over the entire sky, producing a detailed map of the CMB that revealed tiny fluctuations in temperature. To measure the CMB, instruments like the WMAP are designed to detect microwave radiation at frequencies of around 100 GHz. The radiation from the CMB is very faint and is easily overwhelmed by other sources of microwave radiation, such as the radiation emitted by the Earth's atmosphere and the Sunday. To avoid this, instruments like the WMAP are placed in space, where they can observe the CMB without interference from the Earth's atmosphere or other sources of radiation. The measurements of the CMB provide important insights into the early universe, such as the distribution of matter and energy in the universe, the age and size of the universe, and the nature of dark matter and dark energy. The CMB is also a key tool for testing cosmological theories, such as the Big Bang model and the inflationary universe model, and is one of the most important sources of information about the structure and evolution of the universe. 6. The cosmic microwave background radiation shows no evidence of a universe with a preferred direction of spin. There is no evidence that the universe as a whole is spinning or rotating in a preferred direction. The overall structure of the universe appears to be isotropic, which means that it looks the same in all directions. This has been confirmed by observations of the cosmic microwave background radiation, which is the oldest light in the universe and provides a snapshot of the universe when it was just 380,000 years old. The cosmic microwave background radiation is highly isotropic, with fluctuations in temperature of less than 1 part in 100,000 across the entire sky. This indicates that the universe was highly uniform at that time, with no preferred direction or axis of rotation. While individual galaxies and clusters of galaxies can have their own rotation, there is no evidence that these rotations are aligned in any particular direction on a cosmic scale. This suggests that the universe as a whole is not rotating or spinning, at least not in any way that can be easily detected by current observations. The isotropy of the cosmic microwave background radiation and the lack of large-scale structure or preferred directions in the distribution of galaxies and other matter suggest that the universe as a whole is homogeneous and isotropic, with no preferred direction or axis of rotation. If the universe had a preferred direction of spin, we would expect to see patterns in the cosmic microwave background radiation that were not isotropic, but instead showed a preferred axis of rotation. Specifically, we would expect to see a difference in temperature between opposite sides of the sky, with one side appearing hotter than the other. This temperature difference, known as a dipole anisotropy, would be caused by the Doppler effect, which occurs when a detector is moving relative to the source of radiation. If the universe was spinning in a particular direction, then the cosmic microwave background radiation on one side of the sky would appear blue shifted, i.e. shifted towards higher frequencies, due to the relative motion of the detector towards that side, while the radiation on the opposite side of the sky would appear redshifted, i.e. shifted towards lower frequencies, due to the relative motion of the detector away from that side. Observations of the cosmic microwave background radiation have not revealed any significant dipole anisotropy, indicating that the universe does not appear to have a preferred direction of spin. However, it is important to note that current observations have limited sensitivity and may not be able to detect small anisotropies. Future observations with more sensitive instruments may be able to provide more definitive evidence for or against a preferred direction of spin in the universe. However, it is theoretically possible for the universe to develop a preferred direction of spin after the epoch of recombination, which occurred around 380,000 years after the Big Bang and is responsible for the cosmic microwave background radiation that we observe today. However, any such rotation would have to be extremely slow and subtle in order to avoid being detected in the CMB. The reason for this is that the cosmic microwave background radiation provides a snapshot of the universe when it was still very young, and any large-scale structures or motions that existed at that time would have left an imprint on the CMB. Therefore, if the universe had developed a significant spin after the epoch of recombination, we would expect to see some evidence of this in the CMB. That being said, it is possible that the universe could have a very slow rotation that is not detectable by current observations. Such a rotation could be the result of large-scale flows of matter or other astrophysical processes. However, the lack of any observed large-scale structure or preferred directions in the distribution of galaxies and other matter suggests that any such rotation would have to be extremely small and difficult to detect. 7. Why objects spin or rotate in the universe. Objects can spin in the universe for a variety of reasons, depending on their specific circumstances. Here are a few examples. Conservation of angular momentum. When an object undergoes a change in its shape or size, its moment of inertia changes, which can cause it to spin in order to conserve its angular momentum. For example, when a collapsing cloud of gas and dust forms a star, the material that falls onto the star can spin faster and faster as it gets closer, due to conservation of angular momentum. Gravitational interactions. The gravitational attraction between two or more objects can cause them to orbit each other, which can lead to their spinning. For example, the Moon orbits the Earth and is tidally locked, which means that it always shows the same face to the Earth. This is because the gravitational interaction between the two objects has caused the Moon to spin on its axis at the same rate as it orbits the Earth. Electromagnetic forces. Electromagnetic forces can cause objects to spin in certain circumstances. For example, charged particles moving in a magnetic field can experience a force that causes them to spin. Initial conditions. The initial conditions of an object can also determine whether it spins or not. For example, the initial conditions of the Big Bang may have given rise to the observed large-scale structure in the universe, which includes galaxies and clusters of galaxies that can spin. In general, the motion of objects in the universe is governed by the laws of physics, which describe how forces and interactions between objects can cause them to move and spin in different ways. 8. All objects in the universe are linked by gravitational forces and electromagnetic forces. Therefore, the spin of a planet would affect the spin of all other planets and would also affect the central star. All objects in the universe are connected by gravitational and electromagnetic forces, which can cause them to influence each other's motion and spin. In the case of planets, their spin can be influenced by the gravitational pull of other planets, as well as by the tidal forces of their host star. Similarly, the spin of a star can be influenced by the motion of its planets and other objects in its system. These interactions can be complex and can vary depending on the specific circumstances of each object and system. However, in general, the forces of gravity and electromagnetism play a key role in determining the motion and spin of objects in the universe. The mathematical formulas that describe the gravitational and electromagnetic forces that influence the motion and spin of objects in the universe. The equations that describe these forces are known as the laws of physics, and they include Newton's law of gravitation, which describes the gravitational attraction between two objects. The formula is F equals G asterisk, M1 asterisk M2, slash R2. Where F is the force between the two objects, M1 and M2 are their masses, R is the distance between their centers of mass, and G is the gravitational constant. Coulomb's law, which describes the electrostatic force between two charged particles. The formula is F equals K asterisk, Q1 asterisk Q2, slash R2. Where F is the force between the two particles, Q1 and Q2 are their charges, R is the distance between them, and K is the Coulomb constant. These equations can be used to calculate the forces between objects in a system, which can then be used to determine their motion and spin. In practice, however, the calculations can be very complex, especially for systems with many interacting objects. In these cases, numerical simulations using powerful computers are often used to model the behavior of the system. 8. Stars in the galaxies are rotating around the center and also affect the center through the same gravitational and electromagnetic forces. In most galaxies, the stars are rotating around the center of the galaxy, and their motion is affected by the gravitational and electromagnetic forces of other stars and the central supermassive black hole, if there is one. The rotation of the stars in a galaxy can be described by the laws of mechanics, specifically by Newton's laws of motion and the conservation of angular momentum. The gravitational and electromagnetic forces between the stars can also be described by equations like Newton's law of gravitation and Coulomb's law, as well as other equations from electromagnetism and general relativity. Together, these equations can be used to describe the motion and spin of the stars in a galaxy, as well as the motion of the central black hole and the gas and dust that make up the galaxy's interstellar medium. However, modeling the behavior of a galaxy can be very complex, and often requires large-scale numerical simulations on supercomputers. The central supermassive black hole in a galaxy can also spin, and its spin can affect the motion and spin of the stars and other objects in the galaxy through its gravitational and electromagnetic forces. The spin of a black hole can be described by the equations of general relativity, specifically the Kerr metric, which is a solution to the equations of Einstein's field equations. The gravitational and electromagnetic forces between the black hole and the stars can also be described by equations like Newton's law of gravitation and Coulomb's law, as well as other equations from electromagnetism and general relativity. Together, these equations can be used to describe the motion and spin of the stars in a galaxy, as well as the motion and spin of the central black hole. However, modeling the behavior of a galaxy with a spinning black hole can be very complex, and often requires large-scale numerical simulations on supercomputers. The equations that describe the interaction between a spinning black hole and the surrounding matter depend on the specific situation and the level of detail required. Here are some general equations that are commonly used in astrophysics. The Kerr metric describes the spacetime around a spinning black hole. ds2 equals 1, 2mr/ρ2, dt2, 4amr sin2, theta, dt phi plus ρ2 delta dr2 plus ρ2 theta 2 plus r2 plus a2 plus 2mr a2 ρ2 sin 2, theta, sin 2, theta, phi 2. Where m is the mass of the black hole, a is its spin parameter, r and theta are spherical coordinates, phi is the azimuthal angle, and delta and rho are functions of r and theta that depend on the mass and spin of the black hole. Newton's law of gravitation describes the gravitational force between two objects. F equals G, m1 m2, /r2. Where F is the force, G is the gravitational constant, m1 and m2 are the masses of the two objects, and r is the distance between them. The Lorentz force law describes the force on a charged particle in an electromagnetic field. F equals Q, E plus V x B. Where F is the force, Q is the charge of the particle, E is the electric field, V is the velocity of the particle, and B is the magnetic field. These equations can be used to model the behavior of a spinning black hole and the surrounding matter, but the specific details depend on the situation and the level of complexity required. 9. Delayed effect from the peripheral stars to the center and from the center towards the peripheral stars due to the fact that they're hundreds of light years apart. Since the stars in a galaxy are typically very far apart from each other, the gravitational and electromagnetic effects from one star to another take time to propagate through space. This means that there can be a delay in the response of the stars to the gravitational and electromagnetic influence of a spinning black hole or other nearby stars. For example, if a star is orbiting around a spinning black hole, the gravitational force it experiences will depend on the black hole's mass and spin at the time that the force is transmitted. However, because the force travels at the speed of light, the star will only feel the black hole's current mass and spin after a delay equal to the distance between them divided by the speed of light. This delay can be significant, especially for objects that are very far apart, so it is important to take it into account when modeling the behavior of spinning objects in the universe. 10. In the universe there are trillions of galaxies and most rotate anti-clockwise, but we also know that a galaxy's rotation can affect all other galaxies through gravitational and electromagnetic forces. The rotation of a galaxy can indeed affect other galaxies through gravitational and electromagnetic forces, just as the spin of stars within a galaxy can affect the central black hole and other stars. In fact, the gravitational and electromagnetic interactions between galaxies are thought to be one of the key driving forces behind the large-scale structure of the universe. The distribution of galaxies across the cosmos is not random, but instead exhibits a pattern of clustering and filaments that is thought to be the result of the gravitational and electromagnetic attraction between nearby galaxies. As for the rotation of galaxies, it is true that most galaxies appear to rotate in a counterclockwise direction when viewed from a certain orientation, but this is not a universal rule. Some galaxies do rotate clockwise, and others may have more complex patterns of rotation. The effect of one galaxy's spin on the rotation of other galaxies in the universe is a highly complex problem that requires a detailed understanding of the gravitational and electromagnetic interactions between galaxies, as well as the distribution of matter and energy in the universe as a whole. The mathematical description of this problem would likely involve a set of differential equations that describe the evolution of the gravitational and electromagnetic fields over time, taking into account the positions, velocities, and masses of all the galaxies in the universe. The precise form of these equations would depend on the specific assumptions and approximations used to model the behavior of galaxies, but they would likely be highly nonlinear and require numerical methods to solve. 11. The effect of spin of objects that have magnetic fields in the universe would induce electrical energy in all other objects and on the space in between. Whenever a magnetic field changes in strength or orientation, it can induce an electrical current in any nearby conductor. This phenomenon is known as electromagnetic induction, and is the basis for many technological applications such as transformers and electric generators. In the context of the universe, the magnetic fields of spinning objects can induce electrical currents in nearby objects and the space between them. These electrical currents can in turn produce additional magnetic fields, leading to complex interactions between different objects and the surrounding environment. For example, the interaction between the magnetic fields of the Earth and the solar wind, a stream of charged particles emitted by the Sun, can produce the beautiful aurora borealis and aurora australis, also known as the northern and southern lights. The mathematical description of these electromagnetic interactions in the universe is based on the laws of electromagnetism, which are described by Maxwell's equations. These equations describe how electric and magnetic fields interact with charged particles and each other, and are widely used in the fields of physics and engineering to model electromagnetic phenomena. Electromagnetic interactions between spinning objects in the universe can certainly lead to the production and transfer of energy. Whenever an electric current is induced by a changing magnetic field, energy is either absorbed or released by the system. In some cases, this energy can be significant enough to have observable effects. For example, the interaction between the magnetic fields of neutron stars, extremely dense, rapidly spinning stars, and their surroundings can produce intense bursts of electromagnetic radiation, known as pulsar emissions. However, it's important to note that energy is always conserved in these interactions. This means that any energy that is gained by one object must be lost by another, so there is no net gain or loss of energy in the universe as a whole. Energy can simply be transferred from one object to another or converted from one form to another. 12. The effects of interaction of forces in the universe. While gravity is an attractive force, electromagnetic forces can be either attractive or repulsive depending on the charges of the interacting objects. This means that electromagnetic forces can lead to both attractive and repulsive interactions between objects in the universe. These electromagnetic interactions can affect the motion of objects in the universe in various ways. For example, they can cause objects to accelerate, change direction, or even collide with each other. In some cases, electromagnetic forces can even overcome the force of gravity and lead to the ejection of objects from a system. Electromagnetic forces can also lead to the phenomenon of electromagnetic lensing, which is similar to the gravitational lensing caused by the bending of light around massive objects. In electromagnetic lensing, light is bent or redirected by the electric and magnetic fields of charged particles in space. This effect can be observed in various astronomical objects, such as quasars and galaxies. 13. Electromagnetic lensing phenomenon can be described mathematically as. Electromagnetic lensing can be described mathematically using Maxwell's equations, which govern the behavior of electric and magnetic fields. The exact equations used to describe the lensing effect depend on the specific configuration of the electromagnetic fields and the geometry of the system. However, in general, the lensing effect can be understood as the bending or redirection of electromagnetic radiation by the electric and magnetic fields of charged particles. This can be described mathematically using the principles of classical electrodynamics and the laws of geometric optics. For example, the bending of light around a massive object can be modeled using the Schwarzschild metric of general relativity, which describes the curvature of spacetime around a spherically symmetric mass. This metric can then be combined with the equations of electromagnetism to model the lensing effect caused by the electric and magnetic fields of charged particles. The mathematical description of electromagnetic lensing is a complex and multifaceted topic, involving the principles of classical and relativistic physics, electrodynamics, and geometrical optics. Electromagnetic lensing can cause the polarization of electromagnetic waves to change. This is because the direction of the electric and magnetic fields of the waves can be affected by the lensing, which can result in a change in the polarization. The amount of polarization change depends on the strength and orientation of the electromagnetic lens, as well as the properties of the electromagnetic waves. The mathematical description of the polarization change due to electromagnetic lensing is typically more complex than for gravitational lensing, as it involves the interaction of electromagnetic fields with the lensing material. Light waves can be polarized in two different directions, linear polarization and circular polarization. Linearly polarized light waves oscillate in a single plane, which can be oriented in any direction perpendicular to the direction of propagation of the wave. Circularly polarized light waves, on the other hand, are composed of two orthogonal linear polarizations that are out of phase with each other and have equal amplitude. The direction of rotation of the electric field vector of the wave determines the handedness of the circular polarization. The mathematical expression for electromagnetic lensing depends on the specific geometry and properties of the lensing material, as well as the wavelength and polarization of the electromagnetic waves. A simple mathematical formula for a thin electromagnetic lens that focuses light with linear polarization can be described by the following equation. F equals n 1 asterisk t/r, where f is the focal length of the lens, n is the refractive index of the lens material, t is the thickness of the lens, and r is the radius of curvature of the lens surface. This formula assumes that the lens is thin and that the incident light is collimated. The mathematical formula for calculating the polarization of electromagnetic waves after passing through a lens is more complex and depends on the specific lens properties, as well as the polarization and wavelength of the incident light. However, for linearly polarized light passing through a thin electromagnetic lens, the polarization change can be described by a simple rotation of the polarization axis of the light. The angle of rotation depends on the orientation of the polarization axis of the incident light relative to the lens axis, as well as the thickness and refractive index of the lens. This rotation can be calculated using the Jones matrix formalism or other polarization transformation methods. 14. How electromagnetic lenses are created on Earth. Electromagnetic lenses can be created on Earth using a variety of methods, such as using a strong magnetic field to manipulate the path of charged particles or using specially designed materials to control the flow of electromagnetic waves. One example of an electromagnetic lens is a simple cylindrical lens, which can be created by shaping a cylindrical piece of material with specific refractive properties. The mathematical function that describes the focusing action of a cylindrical lens is F equals r slash 2 tan alpha, where f is the focal length of the lens, r is the radius of the cylinder, and alpha is the angle between the axis of the cylinder and the incoming light rays. Polarization can also be achieved in a number of ways, such as using polarizing filters or by passing light through certain materials that preferentially transmit waves with a particular polarization direction. The mathematical formula for simple polarization is I equals I0 cos 2 theta, where I is the intensity of the polarized light, I0 is the maximum intensity, and theta is the angle between the polarization direction and the axis of transmission. 15. Polarization of matter waves due to wave-particle duality of matter. Just like electromagnetic waves, matter waves also have a property known as polarization. Matter waves can be polarized in the same way as light waves, but the mathematical expressions for the polarization of matter waves are slightly different. In the case of matter waves, the polarization is usually described in terms of the direction of the wave vector, which is a vector that describes the direction of propagation of the wave. Matter waves can be polarized in any direction perpendicular to the wave vector. The mathematical expression for the polarization of matter waves is given by the wave function. The wave function describes the probability amplitude for a particle to be found at a particular position in space and time. The wave function can be written as a complex function, and the polarization of the matter wave is related to the phase of the wave function. The phase of the wave function describes the relationship between the particle's position and its momentum. In a polarized matter wave, the phase of the wave function varies in a regular way in a direction perpendicular to the wave vector. The mathematical expression for the polarization of matter waves is more complex than the simple expression for the polarization of light waves. It involves the wave function, which is a complex function that depends on the position and momentum of the particle. The polarization of matter waves can be described mathematically using the Pauli spin matrices. The spin operator can be represented as a 2x2 matrix, which acts on the wave function of the particle. For a particle with spin 1/2, such as an electron, the wave function can be written as a two-component spinor. Psi equals psi, psi, where psi and psi are the probability amplitudes for the particle to be in the spin-up and spin-down states, respectively. The polarization of the matter wave can then be described by the projection of the spin vector onto a particular direction. For example, if we want to describe the polarization of the wave in the x direction, we can use the Pauli X matrix. Sigma x equals 0, 1, 1, 0. The projection of the spin vector onto the x direction is given by the dot product of the spin vector and the x unit vector. Sx equals sigma xs. where s is the spin vector. The probability amplitude for the particle to be in the spin up or spin down state in the x direction is then given by psi x equals 1 plus sx / 2 psi. Psi x equals 1 sx / 2 psi. Similarly, we can describe the polarization of the matter wave in the y or z directions using the Pauli y and z matrices, respectively. 16. Centripetal force and its properties and how it could affect objects in the universe. Centripetal force is the force that acts on an object moving in a circular path and is directed towards the center of the circle. When this force is applied to an object with mass, it causes the object to move in a circular path with a constant speed. However, it is important to note that centripetal force does not cause an object to move in a specific direction. Rather, it causes an object to move in a circular path around a central point. The equation for centripetal force is F equals m asterisk v2/r, where F is the centripetal force, m is the mass of the object, v is the velocity of the object, r is the radius of the circular path. Artificial gravity in a spacecraft can be achieved by using centripetal force. By rotating the spacecraft, the objects inside experience a force towards the center of rotation, which gives the sensation of gravity. This is sometimes called centrifugal force, but technically it is a result of the centripetal force acting on objects inside the rotating reference frame. The strength of the artificial gravity depends on the radius of rotation, the speed of rotation, and the mass of the objects inside. The mathematical formula to calculate the centripetal force is Fc equals mv2/r, where Fc is the centripetal force, m is the mass of the object, v is the velocity of the object, and r is the radius of the circular motion. Einstein introduced the cosmological constant in his field equations of general relativity, which describe the curvature of spacetime due to the presence of matter and energy. The cosmological constant is a term that represents the energy density of empty space, or vacuum energy. Einstein first introduced the cosmological constant in 1917 to explain why the universe appeared to be static, despite the fact that his equations predicted that it should either be expanding or contracting. He believed that the repulsive force of the cosmological constant would counteract the gravitational attraction of matter, leading to a stable, static universe. The mathematical expression for the cosmological constant in Einstein's field equations is r mu nu, 1/2, r g mu nu plus lambda g mu nu equals 8 pi g/c4, t mu nu. Here, r mu nu is the Ricci curvature tensor, r is the scalar curvature, g mu nu is the metric tensor, lambda is the cosmological constant, g is the gravitational constant, c is the speed of light, and t mu nu is the stress energy tensor, which describes the distribution of matter and energy. The addition of the cosmological constant to the field equations modifies the curvature of spacetime in a way that counteracts the effect of matter and energy, leading to a repulsive force that acts over large distances. However, when observations in the 1920s showed that the universe was actually expanding, Einstein abandoned the cosmological constant, calling it his greatest blunder. It was later revived in the 1990s when observations of the accelerating expansion of the universe suggested the presence of dark energy, which can be modeled as a cosmological constant. 17. Entropy of the universe tends to increase naturally due to the second law of thermodynamics that most likely is the natural cause of dark energy that is represented overall as the cosmological constant. Therefore, the expansion of the universe can be modeled through calculation of total entropy, which creates dark energy and is mathematically related to the cosmological constant. We can therefore predict how the universe will expand with time through predicting how entropy will increase in the same amount of time. This proves that the cosmological constant isn't a constant. The second law of thermodynamics states that in a closed system, the entropy, disorder or randomness, tends to increase over time. This means that the universe as a whole tends to become more disordered or random over time. One way to think about this is that energy tends to disperse and spread out, leading to a more even distribution of energy and an increase in entropy. In other words, the universe is moving towards a state of maximum entropy. This is sometimes referred to as the heat death of the universe, where all energy is evenly distributed and no more work can be done. However, it should be noted that the exact nature and timeline of the universe's ultimate fate is still a topic of scientific debate but can be derived from knowing the behavior of entropy. The current value of the cosmological constant is estimated to be approximately 10⁻52 m⁻2, which is a very small value. This value is inferred from various cosmological observations, including the cosmic microwave background radiation, large-scale structure of the universe, and type Ia supernovae. The cosmological constant is thought to be responsible for the observed accelerated expansion of the universe. The rate of entropy increase in a system is generally proportional to time. This is known as the second law of thermodynamics. The rate of increase of entropy depends on the specific system and the conditions under which it operates. In some cases, the rate of entropy increase may be faster or slower depending on the specific factors involved. However, in general, the tendency is for entropy to increase over time in a closed system. The graph that describes the increase of entropy in the universe over time is typically an upward sloping curve, as entropy tends to increase with time in most closed systems. However, the exact shape of the curve depends on the specific system being considered and the rate at which entropy is generated or transferred within that system. In some cases, the curve may be linear, while in others it may be exponential or logarithmic. The possibility that entropy could be the reason for the cosmological expansion can't be underestimated. 18. Dark energy and matter in the universe. Dark energy is a hypothetical form of energy that is believed to permeate all of space and to cause the expansion of the universe to accelerate. It is called dark because it does not interact with light or any other form of electromagnetic radiation, so it cannot be directly observed. The existence of dark energy is inferred from observations of the large-scale structure of the universe and the measurements of the cosmic microwave background radiation. Its nature and origin are still not fully understood, and it is one of the biggest mysteries in modern physics and cosmology. It is currently not well understood if dark energy is directly related to the entropy of the universe. While theoretically there should be a connection between the two, the exact nature of dark energy and its relationship to the observed increase in entropy in the universe is still an active area of research in cosmology. There is currently no evidence to suggest that dark energy is a result of the summation of the rotation/interactions of mass in the universe. Its origin and nature remain a mystery, and it is one of the most significant open questions in cosmology. While the effects of dark energy can be described mathematically, its physical properties are undecided upon. The amount of dark matter in the universe is not precisely known, but it is estimated to make up about 27% of the total mass energy content of the universe. This estimate is based on observations of the large-scale structure of the universe, the cosmic microwave background radiation, and the dynamics of galaxies and galaxy clusters. Dark matter is not thought of as normal matter that we can't see due to electromagnetic polarization in space and time. Normal matter interacts with electromagnetic forces, which means it can absorb, reflect, or emit electromagnetic radiation, such as light. Dark matter, on the other hand, does not interact with electromagnetic forces, or that interaction hasn't been seen except gravitationally. Its presence has been confirmed through observations of the cosmic microwave background radiation and the large-scale structure of the universe. Dark matter hasn't been explained by electromagnetic free energy given by Einstein's equation E = mc2 because dark matter does not interact with electromagnetic forces in the same way that normal matter does, and if it does, such interaction hasn't been noted. If dark matter was simply normal matter that we couldn't see due to electromagnetic polarization in space and time, it's believed that such interaction could be detected in other ways. However, there's a possibility that dark matter is normal matter going backwards in time, hence its light isn't traveling in our arrow of time direction. Other possibilities that dark matter could be a kind of fictitious matter as a result of some kind of reflection of the fabric of space, or perhaps it's matter whose electro-strong nuclear force or electroweak force behaves differently, and thus even the virtual particles in the space around such matter prohibits electromagnetic wave propagation. Whatever dark matter, dark energy turns out to be, I am pretty sure it's as a result of one of the above. Cosmological constant, video. Image of constituents of energy in the universe. Article written by Casually Francis. 16/4/2023